Welcome to Logarithms. This is lesson 1. We'll be understanding what a logarithm is and evaluating logarithmic functions. Our objectives and success criteria for today are to understand that a logarithm is just the inverse of an exponential equation, and that they are. We will also understand applications of logarithms in context, so you will understand how they are used, and you will be able to convert between logarithmic and exponential functions by the end of this lesson. I incorporated a couple of short videos into this lesson to help you understand these concepts. So let's look at our first video that helps us by explaining logarithms.
How does the difference between 0.00000000398 and 0.00000000398 cause one to have red eyes after swimming? To answer this, we first need a way of dealing with rather small numbers, or in some cases extremely large numbers. This leads us to the concept of logarithms. Well, what are logarithms? Let's take the base number b and raise it to a power p, like 2 to the third power, and have it equal a number n. We get an exponential equation, b raised to the p power equals n. In our example, that'd be 2 raised to the third power equals 8. The exponent p is said to be the logarithm of the number n. Most of the time, this will be written log base b of the number equals p to the power. This is starting to sound a bit confusing with all the variables. So let's show this with an example. What is the value of log base 10 of 10,000? The same question could be asked using exponents. 10 raised to what power is 10,000? Well, 10 to the fourth is 10,000. So log base 10 of 10,000 must equal 4. This example can also be completed very simply on a scientific calculator. Log base 10 is used so frequently in the sciences that it has the honor of having its own button on most calculators. If the calculator will figure out logs for me, why study them? Just a quick reminder, the log button only computes logarithms of base 10. What if you want to go into computer science and need to understand base 2? So what is log base 2 of 64? In other words, 2 raised to what power is 64? Well, use your fingers. 2, 4, 8, 16, 32, 64. So log base 2 of 64 must equal 6. So what does this have to do with my eyes turning red in some swimming pools and not others? Well, it leads us into an interesting use of logarithms in chemistry, finding the pH of water samples. pH tells us how acidic or basic a sample is and can be calculated with the formula pH equals negative log base 10 of the hydrogen ion concentration, or H+. We can find the pH of water samples with hydrogen ion concentration of 0.00000000398 and 0.00000000398 quickly on a calculator. Punch negative log of each of those numbers, and you'll see the pHs are 7.4 and 8.4. Since the tears in our eyes have a pH of about 7.4, the H+ concentration of 0.70398 will feel nice on your eyes, but the pH of 8.4 will make you feel itchy and red. It's easy to remember logarithms. Log base b of some number n equals p by repeating the base raised to what power equals the number. The base raised to what power equals the number. The base raised to what power equals the number. So now we know logarithms are very powerful when dealing with extremely small or large numbers. Logarithms can even be used instead of eye drops after swimming.
Hopefully, that gave you a quick overview of what logarithms are, as well as an application of how they're used in real life. Other things use logarithms as well too, like for example the Richter scale for earthquakes. That's a logarithmic scale. Okay, before we go on and look at some examples, like what you saw in the video, I also want to talk about logarithms as inverses. How would you solve, for example, 34 equals 2 to the x? Well, you would solve that by finding the inverse. I'm going to watch another short video that demonstrates this. Before we watch that though, I want you to look at these two graphs down here. Anytime you have an inverse of a function, we know then that the function is reflected across the line y equals x. So for example, if I were to pick this first graph, this blue one, which shows the equation y equals 2 to the x, if I were to pick a point here, and we'll call this point 2 or 1 comma 2, the inverse, remember, just flips x and y. So the inverse of this point would be 2 comma 1, which would be about here. So every point on this blue graph, y equals 2 to the x, has been flipped. The domain, x, and the range, y, have been switched in order to come up with this red graph. And what is this red graph? This red graph is the logarithm. It's the inverse of 2 to the x. This red graph is y equals log base 2 to the x. It's just the inverse. Notice here we have a different base, a base of 3, but it works the same way. So keep in mind that logarithms are just inverses of exponential functions, and you can see it visually by noticing how it is reflected over the line y equals x to get a logarithm or to get an exponential function. Now let's go ahead and link to this video and watch how we might solve.
In a previous video titled, What is an Exponential Function?, we found out how we could model the number of cell phones there are with exactly that, an exponential function. We guessed that there were around 5 in 1981, but then there were twice as many each year. This gave us the exponential function, y equals 5 times 2 to the x power, where y was the number of cell phones there were, and x was the number of years that had happened since 1981. And it allowed us to say things like 23 years after 1981, there were 41 or close to 42 million cell phones, simply by plugging in 23 for x and multiplying it out to figure out what y was. But what if, instead, I said that I was from the future, and in my world, there were over 171 billion cell phones? How far into the future am I from? Now, instead of substituting for x and figuring out what y is, we do the opposite, and we substitute in for y and try to figure out what x is. What I'm left with is an equation that I can use inverse operations to solve for. The first step is easy. I know I can undo multiplication with division. I divide both sides by 5, and I find that 2 to the x is equal to 34 billion or so. But now we need to undo an exponential. Divide? No, division undoes multiplication. Square root? No, square root undoes the power of 2. We need to undo the power of x, but we haven't learned how to do that yet. Enter the logarithm. Logarithms are the inverse operation to exponentials, and they are a quantity that represents the power to which the base must be raised to produce the given number. Okay, that's a mouthful. So let's take a closer look at what I just said. First, they are the inverse operation to exponentials. Just like addition and subtraction undo each other, or multiplication and division undo each other, logs and exponentials do too. Saying this in math might look something like this. If I assume that y plus x is equal to b, I can simply undo the y from both sides with subtraction to get an equivalent statement, x equals b minus y. So I have one statement written with addition and one statement with subtraction that basically mean the same thing. I can do the same thing with multiplication and division. If I say that y times x is b, I can undo the times by y with divide by y, and I get a statement that says x equals b divided by y. So that's a statement written with division. The first one was a statement written with multiplication, but they mean the same thing. They're equivalent. Exactly the same with exponentials. I can have a statement y equals b to the x power. But by taking the log b of both sides, I undo the exponential. The x is now by itself, and on the other side, I have log base b of y. Log base b of y is the logarithmic form, while y equals b to the x is the exponential form, but they both are equivalent statements. Looking at these two forms shows us the second thing I said during the wordy definition. Logarithms are a quantity that represents the power to which the base must be raised to produce the given number. In other words, the answer to a log is the exponent that you raise the base to get the number that you're taking the log of. Okay, now that that detour is over and we have the logarithm in our arsenal, we can get back to figuring out how far into the future I was with my 171 billion cell phones. We were here. 2 to the x equals 34,359,, yada yada. I can now undo the exponential base 2 by taking the log base 2 of both sides, because logs and exponentials are inverse operations. On the right-hand side of the equation, the log 2 undoes the 2 to the x, and I just get x. While on the left-hand side, I now have the log base 2 of 34,359,000,000, yada yada. When you see this, you need to remind yourself that the answer to a log is the exponent that turns the base into the number you're taking the log of. Now, we'll do some tricks and some practice evaluating logs in future lessons. But for now, let's cut to the chase and say that log base 2 of 34 billion whatever is 35 because 2 to the 35th power equals that 34,359,000,000 number. So because 35 is the power that turns the base of the log into the thing I'm taking the log of, that is my answer.
Okay, now that you understand that logarithms are just inverses of exponential functions, let's practice switching back and forth. Let's start with an exponential function and let's turn it into its equivalent inverse function, the logarithm. Well, how do you do that? Well, the way you do it is we know we're going to turn it into a log, so we know we're going to have a log, so we would write log. Now, notice that we have a base of 4 right here. This is our base. Our base always stays our base. It never changes. So we have log base, think of basement, it's down below, log base 4. So what do we do now? Well, we know that the logarithm is always equal to the exponent, and the exponent is 3. So the logarithm of our base, 64, has to be equal to 3. So think about what we did to switch this to a logarithm. We kept the log here, and we kept this base, and we just switched the exponent and the number. And that's all we did. Let's try the next one. So we have 10 to the negative 2 equals 1 over 100. It looks tricky, but if we just follow the same rules, we should be fine. So we know we're going to change it to a log, so we write log, and we keep our same base, 10. And now we just switch these two, because we know that the log base 10 of a number is going to be equal to our exponent of negative 2. So log base 10 of 1 over 100 has to be equal to negative 2, and that's all there is to it. Now what you'll notice is that anytime you have a base 10, like was mentioned in a previous video, you can write that as just log. If you don't have a base here, it's understood that you have a base of 10. And your calculators usually always have base 10 as a button. All right, pause the video and try this third one on your own. All right, so hopefully you wrote log, you kept base 5, and then you switched the exponent with the number. So we would have log base 5, 75 equals 3. And then finally for this last one, this e is the natural number. You may or may not have seen it before, but we can still do the same thing. We can write log base e. We'll go ahead and switch the exponent in the number. So we have log base e, 7.389 equals 2. Now, just like this log base 10, how we can write this as just log base e is a natural number, so we can write it as the natural log, ln. So instead of writing log base e, we can write natural log 7.389 equals 2. It's the same thing. And your calculators will also have a natural log button. All right, great. Let's do one more set of practice. This time let's go from a logarithm to an exponent. Okay, let's just apply what we already know. Well, here's our base, and it stays our base, so we'll start with that. And then we're just going to switch these two. That's what we always do. So 2 to the third has to equal 8. And we know that it does. Let's try the second one. 3 is our base. We're just going to switch these two numbers. So 3 to the negative 2 has to equal 1 over 9. And if you remember your properties of exponents, anytime you raise a number to a negative power, it means take the reciprocal of that number. So that would be 1 over 3 squared. And 3 squared is 9. All right, let's try this third one. Pause the video and see if you can do this one on your own. Okay, well hopefully you wrote 4 as our base. You switch these two, so you get 4 to the third equals 64. All right, remember, this ln just means natural log. In other words, it means log base e equals 1. Okay, well let's just follow our same logic, although I did leave off the other e. There's two e's there actually, so we have log base e, e. Notice how this e is next to the natural log. Natural log by itself means log base e. So we have log base e equals 1. If we follow our rules, we keep our same base e, and then we switch the e and the 1. So e to the e power, e to the 1 power is equal to e, which we know to be true. Anything to the first power equals itself. All right, how about this last one? What is our base? Again, I don't see a base just like up here. Well, we know that our base, if it's not shown, is going to be 10. So this is really log base 10 to the 1000 equals 3. Let's go ahead and apply our rules. So we would use our base and keep it the same, and then we would switch our numbers. So we would have 10 to the third equals 1000, which again we know to be true. And that concludes our lesson on understanding and evaluating logarithms. So at this point, you know you have successfully watched this video if you understand that a logarithm is the inverse of an exponential equation. And you can also understand some different applications of logarithms, and you will be able to convert between logarithmic and exponential functions.